When starting a company, there are often a range of strategic decisions which must be taken, which can have a very real impact upon future operations. Physical options, such as location, can be often very well understood. However, things like the actual design of a piece of software are much more poorly understood and can have a very real impact further down the line. Today, we're going to understand how these decisions can actually end up pigeonholing a company and also understand some of the core assumptions that lie behind them. So Johannes, today we're talking a bit about how poor software design can actually impact upon a company. So what are some of the challenges that you've seen?
The first is that software design is critically important, and for supply chains and modern supply chains, they run on software. You have trucks, you have machines, you have conveyor belts, but also you have large chunks of software, your ERP, your MRP, your WMS, your OMS. You have so many layers, your EDI. You have so many layers of software, and literally modern supply chains don't run without software in large quantities. And the interesting thing is that when I discuss with clients of Lokad, they end up frequently they are struggling against the I would say applicative landscape of their supply chain. So there are a lot of software related problems, but they are not necessarily like bugs, oh, this piece of software crashed. That's the easy case, that the software is crashing, it's easy, it's obvious, you need to fix that and done. I would say design problems are much more pervasive. It's not super obvious, but things are sluggish, things are not intuitive, things are slow, it takes forever to configure the damn thing. Every time you want to change anything, it takes forever again. And when you try to do some kind of root cause analysis, I frequently witness that the problems are actually software design problems, where fundamentally the core fundamental decisions were made about the design of the software, and it just completely mismatch the actual reality of the given supply chain of interest.
Okay, so what sort of features of a software's architecture can be so important then? What are some of the challenges that you've seen with your clients?
Let's say, for example, real time. Many systems, I would say when I say real time, there is no such thing as absolute real time. The speed of light is finite, so in this world of the internet, for the information to go back and forth, it takes dozens of milliseconds. So there is no such thing as zero delay, even at the light of speed, when you operate at a global scale with pieces of software all around the world. But let's say most, I would say, of the supply chain software nowadays are actually geared toward real-time stuff. What do I mean by real-time stuff? I just mean that, for example, if you decide to pick one unit on the shelf, it's going to decrement the stock level, immediately. Okay, it looks fine. It looks like a very reasonable thing. I'm doing one picking operation. I take one unit, and as soon as I have physically taken the unit, I have decremented the stock level for the counter on the shelf by -1. Looks very reasonable. Unfortunately, as soon as you have, when you have this kind of software that is designed for real time, so technically we are going to speak about, a relational database that is going to be the backing of this system. It means that any sophisticated calculation is going to be a big pain to operate in the software. Why? Because if your software is designed to be super fast for super simple operation, having a complex operation, and what do I mean by complex operation? A forecast, a network-wide analysis, or anything that is not like a very local data-wise, a very local operation where you just need to modify one SKU, one location, one something. As soon as you have data-wise a moderately complex amount of processing, it's going to be a struggle because your software is designed for very swift, small operation. And if you have like a big granular operation, it's going to slow down everybody, including things that should be like super fast, like just scanning a barcode and doing beep I have scanned, you can proceed to the next item.
And how obvious are kind of some of these challenges? Because you've got to sympathize with a supply chain practitioner. I mean, there's a lot going on. And with a lot of time with this software, there's a hell of a lot going on under the hood. So how obvious is it that some of these challenges are out there?
So it's not obvious because usually this is not like an obvious bug where your system crashed. It's more like death by 1,000 cuts. So let me illustrate. You have this system that is supposed to be real time. So when there is something that is scanned on a high-speed conveyor belt, you should be able to beep items, 3 items per second or something. You should be able to be really fast and have like milliseconds response time. Now, what is happening if once in a while you have a calculation that just takes a few seconds instead of taking milliseconds? Well, if you just have one operation, once in a while that takes a few seconds, if your real-time system is nicely designed, probably most of the other operation will stay super fast. So it doesn't hurt that much, except if you're not lucky and at the same point of time you have like 10 different operations that takes multiple seconds to compute that just absorb at this specific point of time all the computing resources. So what will happen? The system that was supposed to be able to scan and give you a beep of feedback under a millisecond, suddenly this thing is going to take 1 or 2 seconds. It's not terrible, you can live with it, but suddenly once in a while you have this thing where you were expecting something that was like lightning fast, suddenly it's like 2 or 3 seconds of delay. And by the way, you can see that at sometimes I've seen this sort of patterns even in my local hypermarkets where there is the point of sale, they beep stuff, it's very fluid, and at some point they just beep something and 3 seconds happen and then beep. Okay, so here you have literally a real-time system that was kind of clogged into a non-real-time operation of some kind. I have no clue what it was. Maybe it was a Windows update. I don't know. The sort of weird stuff that happens that slow down the machine. But literally, in a real-time system, you're not allowed to do anything smart or anything complex because that's literally going to degrade the super fast operation you want to carry. And when I say death of 1,000 cuts, is that the first time you do a non-real-time thing in a real-time system, probably nothing bad will really happen, because first you're very small scale, it remains rare, so you're kind of okay. But the problem is that you pile up more and more non-real-time stuff, suddenly you end up with a situation where those problems that were very infrequent, they start to become more frequent and more frequent until they become super, super frequent. And then people are just going nuts and say, well, this thing where I'm literally, why is this conveyor belt not working faster? It could, and the answer is because there is a machine that is supposed to scan the barcode. We need to wait for the system to answer, and I've seen situations where literally it was taking like half a minute for the system to answer back after scanning a barcode. And actually it was about printing something to put on the box. But literally, so the conveyor was literally limited by the speed on which the system could just deliver the order to the printer to print something on the box. And literally they had people that were just waiting for the printer to print. So you have plenty of design choices that where you need to get the core choices very in ways that are deeply aligned with the problems that you're trying to solve.
Okay, so what you're sort of saying is that from a kind of design perspective, there's a lot of core assumptions that are made, and if these core assumptions aren't actually met, that's when there's sort of troubles that can come on down the line.
Exactly.
So in a supply chain scenario, and a supply chain piece of software, what are the key core assumptions that are being made, and which are the ones that you've kind of observed as not really working?
I mean, there are many ways. First is what is the time scale you want to operate in. So, and here we have things that need to operate from sub-millisecond response time. So that's what you need to literally drive a conveyor belt, millisecond by millisecond. To decisions where you need to think a decade ahead. Again, placement of factory. So you have like, and every time you add an order of magnitude, you change fundamentally software. So sub-millisecond is one type of software. From 1 to 10 milliseconds, it's going to be another type of software. From 10 to 100 milliseconds is going to be another type of software. That's basically the typical ERP type of software where you can have response time from 10 to 100 milliseconds. From 100 milliseconds to 1 second, that's pretty much the sort of things that you can get with a web app. So that's typical response time from a web app. Then probably if you are starting to think, from 1 minute to 10 minutes ahead, suddenly you enter a realm where you're not real time anymore. But the news is that you can be you can start to do like fancy calculation. So let's say, for example, Waze, who is helping you to navigate through a city and giving you a route. It's typically this order of magnitude. They need to be able to give you a route within half a minute. But it doesn't really have to be real time. You prefer if that Waze takes half a minute to give you a route that is going to save you 20 minutes, as opposed that the system just gives you in 1 second a very crappy route where you're going to waste 1 hour. So obviously, that's the sort of things. If you are optimizing, a route for a truck and deliveries, you can typically take multiple minutes to get the results. Again, even if it's kind of you need to interact in a way that is smooth with the truck driver. Once you've told the truck driver to go to this location, it will take for minutes for this person to reach this location. So you have multiple minutes to decide, for example, what is going to happen after they reach this location. So again, we are changing on time scale. At Lokad, we are typically more on the time frame from 1 day to a year. So again, that's a time frame where you want to think in terms of days. That's typically a sweet spot of Lokad. And again, it means that we can pretty much ignore all the things that are before. But then if we go beyond 1 year, we end up with something that looks like supply chain design, and suddenly it's not a game of numbers anymore, it's more like map-centric, and we change the problem.
Let's talk a little bit more about the implementation of a piece of software. One of the things that's of interest is whether a piece of software is single tenant or multi-tenant. So what are the key differences between these two routes?
So that's a more technical angle, and most companies are not necessarily super familiar with that. But for a software editor, it's very critical. So the difference between single tenant and multi-tenant is literally how many clients are you going to serve with literally exactly the same piece of software. If you are multi-tenant, like Lokad, it's literally the same software that is serving all our clients, period. We have only one version deployed online at any given time. We update this software on a weekly basis, but it's just one piece of software, which means for Lokad, one code base extra. The other way, which was, by the way, what was the favorite way before the advent of SaaS, is a single tenant. Single tenant is literally what SAP does, which is you have one client, you just give them one copy of the software. And it means that when you have like one client and one copy of the software, frequently what happens in enterprise software is that large clients tend to get versions that are customized, sometimes lightly, sometimes heavily, but fundamentally customization happen. And then for the software company who is producing the software, it means that suddenly you end up with many variants of your software that just happen to be running at the same time, which is a big operational problem, because it means that if there is like a bug that happened on one version, you have to fix this version, but you have to make sure that the bug is also fixed in all of your other versions. And by the way, this is a problem where for the software companies, you have like anti-economies of scale, where the bigger you are, the more problem you have with your versionings. By the way, it's a problem that is very severely impacting Oracle, for example. With the Oracle database, they have like plenty of heavily customized versions that are tuned for performance. And I have no secret insider, but from just public information, you can see that literally in some multiple engineering divisions at Oracle are struggling with the fact that they have many variants of their software out there. Obviously, Oracle is very rich. They have tons of engineering capabilities, but nonetheless, it remains a big, big challenge. So, so single tenant gives you the option of per client customization, but then you have to deal with per client overhead. Multiple tenant gives you the fact that you have one code base for everyone, no customization, but in exchange you can evolve much faster, and also you have much less security problem.
So would you say that the marketplace is very much moving towards that kind of SaaS model? And why is it that that model is so much better? Does it give a greater degree of flexibility for the company?
I mean, yes, over the last decade, pretty much all the serious software editors have moved toward multi-tenancy. Even, classical, traditional desktop application that were, because obviously if you're a web app like Lokad, being multi-tenant is fairly straightforward. You redeploy the stuff on your own systems. Okay, done. Obviously, when you have software that operates on client machines, like let's say your browser, let's say for example, Internet Explorer or Google Chrome, it's more complicated because you don't have control over your client machines. But guess what? Software editors, what they have done, they have switched toward the evergreen strategy. So for example, Google Chrome doesn't ask you anymore the question about updating the browser. When Google decides that your Chrome version is outdated and need to be replaced, Google update your browser at a distance. Obviously, the next time you connect to the internet and whatnot, they can't, magically update your software if you don't have internet connectivity. But assuming that you have internet connectivity and you've not done any specific shenanigans with your machine to specially prevent the upgrade, basically the upgrade will happen, basically without your, I would not say without your consent, but without your intervention. It will just upgrade itself. And when you look at what Microsoft is doing with Office 365, same thing. In the past you had like a series of Microsoft Office version where you were moving from one Excel version to the next. Nowadays, it's it's on demand, and Microsoft takes care of upgrade. You have like a subscription. The software is installed on your machine, but it can just upgrade itself to the next version. And unless you deactivate the upgrade options, etc., Microsoft is just upgrading all the desktop apps precisely to mitigate the problem of having many versions of the same software.
Okay, let's talk a bit about Lokad then. You said that there were certain core assumptions that have to be made in a software design that can really impact upon future operations. So what were the core assumptions that you made here at Lokad?
Tons of them. But before I go into the core design assumptions, I would have a note is that if you met a software vendor that tells you, oh, my software, we are capable of everything. We didn't make, the software assumption. Or if they give you only, I suggest, when you met a software vendor for your supply chain, ask them what are the core assumptions. And if they tell you, something like vague stuff that are vague and positive, like, oh, we are designed for security. Great. Yeah, me too. We're designed for speed. Yeah, me too. Absolutely. We are designed for cost efficiency. Yeah. This is sort of super vague, absolutely positive things, which are, when we discuss about design, a design is a design standpoint is a trade-off. It's something that has positive aspects and negative aspects. So, and again, if you can discuss with a software vendor and all they can give you are the positive aspects, it's probably that they don't even understand the nature of software design in the first place. So what are the core design assumptions that we built into Lokad? The first was a batch processing mode. So what does that mean? That means that what we want is to be able to crunch tons of data, big data like, and to do very smart calculation. Obviously, because we want to, and we say we prefer to be very smart as opposed to be very, very fast. Which means that we want to have calculation that are typically executed within minutes, but the fact that they can be executed within seconds is kind of a bonus. But if we can't, it's not such a big deal. We prefer to have like better numbers, even if it takes a bit of time. By the way, it's not because there are parts at Lokad that are real time. It's just a presentation of the results. So maybe we will need like half an hour to do a massive computation. But when you want to access those results, then it needs to be real time. But it's pre-computed. But you see, that was a core design assumption. No real time, all is batch. And the reason is that we want to be able to be very expressive and very powerful, and thus be as smart as we can for, I would say, network-wide analysis. So that's one core assumption. Another one was we wanted to have multi-tenancy. Obviously, nowadays, most people are doing that, but there are still companies that are, especially in the enterprise space, that are, I would say, lagging behind. And I would say multi-tenancy done with all the capabilities offered by the cloud. So for example, that means that we want to have scale out capabilities rather than scale up. Again, a lot of people would be kind of confused by what do I mean by scale up versus scale out. The question is that if you want to process tens of terabytes of data, can you do that by just piling up tons of small machines, or you need to have like a super mega computer to do it?
If we start wrapping things up for today then, what's kind of our main conclusion? Is our conclusion that in terms of the data we have out there, in terms of making the choices of that software, it can very much pigeonhole what you do in the future, so you need to fully understand those choices that you're making?
Yes, I mean, although we have been cycling around the subject a lot, my suggestion would be for supply chain practitioners is to be more aware of the core assumption, the core design assumption that are, that are characterizing their own applicative landscape. They have many apps, and can they give me, half a dozen of critical, core design assumptions that kind of explain the ins and outs of the product? And it might sound like super technical, like why would you be so technical when it comes to understanding the product? And I would say, well, if you don't understand those core design assumptions, you are going to suffer a lot when you realize that you're attempting to do something where by design, this is not going to be, a good product for that. And frequently I see many companies where literally their problems are emerging from, I would say, mismatch between the design of the software and what they're trying to do with it. And vendors try to be very confident. As a vendor, you're trying to sell your software. You want to act confident and to tell, oh, my beautiful piece of supply chain software is going to be always nice, in all situations, and we got you covered. But the reality is that if a client is going to use your piece of software for something that is outside, your design capabilities, you can't duct tape the thing. You can't just add a feature. The software engineers on the back are going to tell you, boss, sorry, can't do. It's going to be hell.
Okay, we'll have to wrap it there, but thanks for your time. That's everything for this week. Thanks very much for tuning in, and we'll see you again next time. Bye for now.